yesterday's topic, okay, about the imperfection or defects in crystals, as well as in metal, as well as ceramics. Okay, so for today we will continue on the crystalline imperfections. Okay, so I think you already understand how to apply Hume or rotary rules. Okay, to determine the solid solidity between two elements or two compounds. Okay, either metals or non-metals. Okay, so everybody, I hope everybody can hear my voice. So that uh, okay. So for example two. Okay, I hope that everybody can do this one. Okay, before we start the next part of this chapter. Okay, the for the example two. Okay, calculate the radius of the largest interstitial void in the FCC gamma ion lattice. Okay, the atomic radius of the ion atom. Okay, sorry, this one it should be the ion atom. The ion atom. The ion atom is 0.129 nanometer. Okay, in the FCC lattice, and the largest interstitial voids occur at half and 0, 0. Okay, 0, 1, 0, half, 0, 0, 0, half, etc. types position. Okay, can you calculate the radius of the largest interstitial void? Okay, so what you have to do is you have to determine the plane. Okay, so if you look at here that the plane is 1, 0, 0 from the figure below. Okay, this one. Okay, this plane. Okay, and you enlarge this one, we can see the atom. Okay, so this one, this is a large atom, as well as the small atom. Okay, this is iron. Okay, and then there's interstitial voids. Okay, here. Okay, so what you have to do is calculate the radius. Okay, the largest interstitial void. Okay, what is the radius or r? Okay, this one, because there is an interstitial. Okay, there is a defect there. So what you have to do is look at here, that is the position of the position of the what is it, the interstitial atom is, look at here, this is the position. Okay, okay, the position is 0, half, and 0 position coordinate. Okay, with the 100 lattice plane. Okay, so what you have to do for the ions. Okay, the radius is we use a symbol big R or large R, while for the interstitial atoms we use small r. Okay, so what you have to do, this one. Okay, since we want to calculate the radius of the interstitial voids, which is r, small r. Okay, what you have to do is 2r plus, okay, this one, right? 2r plus 2r equal to E. Okay, so this one, the length is A. This one also, the length is A. Okay, so this is going to be equation number 1. Okay, so from this figure we can get, okay, 2r square, okay, plus equal to half A. If you remember trigonometry, okay, from this one, to get the 2R, right? Okay, this one. You enlarge this position. Okay, plus of A. Okay, okay. So this is equal to half A to R. Okay, so this is gonna be equation number 2. Okay, so 2R is gonna be 1 divided by square root 2. Okay, A. So it's gonna be question number 3. Okay, can you solve this one? So please solve this one. Okay, by combining equation 1 and equation 3 to get R. Okay, what is R? Can you calculate and give me the answer? You can put in the chat box. Okay, please do now. What is so from this example you have to know the information of the about the milling indices or the plane. Okay, from the previous chapter in chapter 3. Okay, so this is important to know the position of the voids or either atoms. Okay, the position of the interstitial atoms or substitutional atoms. Okay, so if it's given the uh, what is it the elements, okay, or the unit cells at the in BCC, FCC or SC, so you have to determine the position, okay, for the defects, like such as like interstitial or substitutional. Okay, so please determine the radius, okay, for the interstitial atom. Give me the answer. Okay, I already make the what is it? Give the hint. Okay, so just follow this step. So I already give the step and solve it by combining equation 1, okay, as well as equation 3 and determine small r. What is the radius of the interstitial atom? Okay, before we move to the crystalline imperfection. 0.053 nanometer. Is that all? Yes, that is correct. 0.053 nanometer. Okay. So the answer is R equal to 0.053 nanometer. Thank you, Izato. Okay. So this equation, actually, chapter 4 and chapter 3 is aligned each other. Okay, so you cannot separate. Okay. Since also chapter 4 is about the metals as well as crystal compound or crystal materials. Okay. So any questions about these examples? So I hope everybody can okay. Okay. So if no questions, let's we move to the next part, which is crystalline imperfections. Okay. So as I told you in the previous class that in reality crystals are never perfect. Okay. and there are contains various type of imperfection or irregularities, defects that affect many of their physical and also mechanical properties. If you look at here in the ideal structure, okay. Usually this gonna affect many important engineering properties of materials, okay, such as color-formability alloys, okay, the electronic conductivity of semiconductor, okay. What else? Migration of items in alloy, okay, the corrosion of the metals, and the crystal lattice imperfection are classified according to the what is it, the geometry as well as shape. Okay, if you look at here, that they have four types of the crystalline defects, three main division actually, 0D, or we call it as a point defects. Example is vacancy. Or 1D or line defects, we call it a lattice dislocations. Okay, so some part is a dislocate. Okay, 2D or area defects. This is interfacial defects. Okay, this is the example for each defect. Or other example is like external surface, grain boundaries, okay, twins, low angle boundaries, okay, high angle boundaries, twists. Twists are almost similar like lattice dislocation. Okay, stacking faults, void. A void is also like a vacancy. Okay, precipitate. Okay, that is an example of 0, 1, and as well as 2D defect. Okay, so please remember that one. Please take note what I already told you. Okay, about the example of the 1, 2, as well as 2D defects. Okay, so three-dimensional microscopic or bulk defect also we can include. Okay, this one 3D or volume defect. Okay, for example is crack, pores, and also foreign inclusion. Okay, that is the 3D defects or volume defects. Okay, look at here is a much larger. Okay, so what is the difference, or how can we distinguish this 0D, 1D, 2D, as well as 3D? Okay, so we can see from the size of the defects, point, line, planar, as well as volumetric defects. So if you look at here, that this is a point defects, 10, negative 14. Okay, this is a dimensional range or scale. Okay, for different class of the defects. So atomic point defect is a much larger, negative 10. This is a vacancy. Vacancy is a 0 point defect also. Okay, and this one is dislocation. Dislocation is between, I think is this one is 8. This one is 4. Okay, around below than 10, negative 10. And this one is around 10, negative, this one 4. I think this one is 10, negative 5. This one 10, negative 9. Okay, this is what we call is a line defect or dislocation, the size. So for the grain and twins boundaries, voids as well as precipitate, which is we call it as an interfacial defect. This is a precipitate is a, what is it? Okay, interfacial or 2D. Okay, this one is 2D. Okay, this is around 10, negative 8 to 10, negative 2. Okay, this is a 2D, 1D, this is a 0D. Okay, so and the largest one is more to volume defects, pore crack as well as inclusion. This is volume defects, 3D. So 0D, 1D, 2D as well as 3D. This is volume defects. This is much larger. Okay, so we can see, I think, because it's a like a volume, right? Like a crack. Cracks we can see with our bare eyes. Okay. Okay, this is in terms of the scale. Okay, so type of point defect in metals, generally we can see the point defects. Okay, which is localized to a few atom site. This is a point defects. Okay, and atom missings caused by the distortion of planes. And this is vacancy also we can find in the metals during the maybe solidification. Self interstitials. Okay, so some atoms move into the void or empty space. Okay, atom of the same kind of the host atoms occupy the interstitial site. So it causes the distortion also. Okay, and some impurities, interstitials, okay, impurities atom, okay, in substitutional or interstitials, okay, present in metallic or covalently bond crystals, can be substitutional or interstitials, okay. So this is a type of defect that we can found in the metals, okay. So for the point defects, which is a vacancy, is a form due to the missing atom. So you have to remember that's why we call it as a vacancy or void. Okay. So 1 in 10,000 atoms during crystallization or mobility atoms. So the energy formation is about 1 electron volt. Okay. So vacancy can move by exchanging position in their neighbors. Okay. Also mobility of vacancy result in the cluster of the vacancy. So another process which can cause the vacancy is like rapid cooling, okay, plastic deformation as well as particle bombardment. Okay. So in terms of the interstitial interst, interst, interstitial sites or occupiers of the interstitial site. Okay, this is also the point defect. So by using the process is such as like irradiation. Okay, it can cause distortion. So if you look at here, this is the difference, right? Different atoms, right? Okay. So this is we already defined what is the interstitial. Okay. Okay. So in terms of the charge about the related with the cation or anions, okay, it can cause also the point defect in the ionic crystals. Okay. How are they different from those in metal? So this is in ionic crystals. So it is a complex as electric neutrality have to maintain delta Q equal to 0 because they want to maintain the neutrality. Okay. So if you look at here that the green one is the Frankel defect. Okay. Created when the cation move to the interstitial site. Okay. So this one, if you look at here, this is become a vacant since the atom is moved to the neighbor site. Okay. So this is a Frankel defect. Related with the movement of the cation. Okay. For the Scotchy defects, okay, Scotchy defects, two oppositely charged ion are missing. Okay, a cation or an ion deficiency is created. Okay, for example, this one. Okay, this is a vacant. This is a vacant. Okay, this is a Scotchy defects. Impurity ions are also considered as a point defect in ionic crystals. This is also, we call it as a stoichiometry defects because they want to maintain the neutrality. Okay. So the other examples, okay, for the stoichiometry defects, okay. For other examples, we look at here. This is in ceramics, okay, Frankel and Scotchy defects to maintain one cation and ion ratio. Okay, this is also, we call it a stoichiometry defects. Okay, so if you look at here, okay, if you look at that non-stoichiometry, okay, cation and ion ratio is not equal to 1:1 occur when one ion exists in multiple valence states. If there is a ferrum ion 2 plus, ion 3 plus, copper 1 plus, and copper 2 plus. Okay, in ferrum oxide, okay, the charge of ferrum ion is plus 2. So if we have a ferrum 3 plus ions, then ferrum 2 plus vacancy is required to maintain the charge unity. So that means since there is a ferrum 3 plus, okay, here, okay, so ferrum 2 plus need to be vacant, okay. So this position should be vacant. Initially, okay, there is a ferrum 2 plus here, okay, there's a ferrum 2 plus here. Okay, since they want to maintain the stoichiometry 1:1, okay, if there is a ferrum 2 plus here, the stoichiometry is not going to be 1:1. So in order to maintain the stoichiometry balance, okay, in order to maintain the stoichiometry balance 1:1, okay, so this one should be defects. Okay, this is to balance the or maintain the charge neutrality. Okay, so this unbalanced number of ion, we call it as non-stoichiometry defect. Okay, so if you calculate, it's going to be balanced, the stoichiometry. Okay, since there is a F3 plus, Fe3 plus, and there is a vacuum here. So if you calculate here, all the ion, okay, this one, all the ferrum, okay, with the oxygen, so you can see it's a maintain cation and ion ratio 1:1:1. Okay, so this is another example also for the Frankel and Scotchy defect, or we call it stoichiometry defect, non-stoichiometry defects. Okay, so you have to remember that one. Okay, so another point defects is the impurity ions. Okay, the reason is to satisfy the charge balance or electron neutrality. Okay, so how they accommodate in the crystal lattice. Okay, for example, this one atom and ion cations. Okay, is also can cause the non-stoichiometric defects. Okay, so cause and balance number of ions. Okay, this is a impurity ions. Okay, so there's a, let me look at here. This is a substitutional and ion impurities, and this one is a cation impurities. So just to maintain the charge balance. Okay, or stoichiometry balance. Okay, so this one's cation impurities. Okay, as a simple like this is I think this one. Okay, cation impurities. Okay, to maintain the balance, the electron neutrality. So what point defect occur when Ca2 plus substitute to Na plus? Okay, so if you look at here, okay, if we replace this Na with Ca2 plus, there is a vacuum here. Okay, this is because we want to balance the charge. Okay, or same stoichiometry. Okay, so this is favorable. Okay, if you put this one also Na, okay, or 2 plus, so it's not gonna be balanced. Okay, so in order to balance, okay, so we need to one space or vacant here. Okay, so charge will be balanced if another plus one charge is eliminated. Okay, charge can also balance if we add one Cl ion to the lattice. Okay, so we can either we remove or we want to add. Okay, okay, so in terms of anions, okay, anion impurities, similarly, if we replace this Cl minus with the O2 minus, there is an ion vacancy. Okay, because we want to maintain the electron neutrality. Okay, so this is a type of the stoichiometric defects or anion and cation impurity. Okay, so let's see, we watch this video. Okay, I'll stop sharing this one. I want to share this one. Wait, share the video. Okay, this is about the defect in solid. Okay,
Defects in
boleh
solids.
dengar tak?
In this module, you will learn about
Anyone can
the
respond?
various
Can
types
you
of
hear
point
the
defects present
sound?
in the crystal lattice of solids. Crystalline solids have a regular arrangement of the constituent particles. However, this regular arrangement is sometimes interrupted by certain defects in the crystal, such as point defects and line defects. A defect arising due to the irregularity in the arrangement of the constituent particles around a single lattice point is referred to as the point defect. On the other hand, a defect arising due to the irregularity in the arrangement of the constituent particles across a row of lattice points is referred to as the line defect. In this module, we are going to explore the point defects, which are of three types: the stoichiometric, non-stoichiometric, and impurity defects. The stoichiometric defects are so called because they do not bring any change to the stoichiometry of the solid. These defects exist in the crystals of non-ionic as well as ionic solids. In the case of non-ionic solids, the stoichiometric defects exist in two different forms: vacancy defects and interstitial defects. A vacancy defect arises when a constituent particle leaves its lattice site, creating a vacant site in the crystal lattice. Alternatively, an interstitial defect arises when a constituent particle occupies an interstitial site in the lattice. On the other hand, in case of ionic solids, the stoichiometric defects exist as Frankel defects and Schottky defects. In both the Frankel and Schottky defects, the electrical neutrality of the substance remains maintained. Frankel defects arise in the ionic crystals having large difference in the size of the constituent ions. In such defects, the smaller ion dislocates from its lattice site to an interstitial site. Schottky defect, on the other hand, arises in ionic crystals having constituent ions of similar size. In such defects, equal number of cations and anions leave their lattice sites and create vacancies in the crystal. So far you have learnt about the defects that maintain the stoichiometry of a crystalline substance. However, there are certain defects that change the stoichiometry of a crystal. These defects are called non-stoichiometric defects. Non-stoichiometric defects are of two types: metal excess and metal deficiency defects. The metal excess defects arise due to two reasons: the presence of anionic vacancies in the crystal or the presence of extra metal ions. Let's first understand the metal excess defects that arise due to anionic vacancies in the crystal. When sodium chloride is heated in the atmosphere of sodium vapors, then some sodium atoms get deposited over the surface of the crystal. Some of the chloride ions diffuse from the lattice sites to the surface and combine with the sodium atoms to form sodium chloride. The electrons lost by the sodium atoms diffuse inside the crystal and occupy the sites vacated by the chloride ions. These sites are called the S centers. Such a crystal of sodium chloride, therefore, has an excess of sodium metal and thereby develop the metal excess defect. Let's now consider an example to explore the metal excess defects that arise due to the presence of extra metal ions. When zinc oxide is heated, some oxygen gas is released from it. The remaining extra metal ions and free electrons produced during the reaction occupy the interstitial sites, thereby developing the metal excess defect in the crystal. Now that you have learnt about the non-stoichiometric metal excess defects, let's learn about the second type of non-stoichiometric defects, the metal deficiency defects. The metal deficiency defects arise when a crystal becomes deficient of the metal on losing some metal ions from their sites. In such a case, to maintain the electrical neutrality, some of the remaining cations acquire extra positive charge by moving into the higher oxidation state. For example, in the crystal of ferrous oxide, a few ferrous ions move out from the site, resulting into a non-stoichiometric defect. Some of the remaining ferrous ions acquire higher oxidation state and become ferric ions. Let us now learn about the last type of point defects found in crystal lattices of solids, the impurity defects. An impurity defect arises when a cation leaves its site and some foreign cation occupies the vacated site. Such defects are found to occur in crystal lattice of sodium chloride when some lattice sites vacated by sodium ions are occupied by the strontium ions. To maintain the electrical neutrality of the crystal, one strontium ion replaces two sodium ions. So, half of the vacated sites are occupied by the strontium ions while the other half remain vacant. Let's summarize what you have learned in this module. On the basis of their locations, the defects in the crystal lattices are divided into two types: point defects and line defects. Point defects are the irregularity in the arrangement of constituent particles located around one lattice point, while line defects are the irregularity in the arrangement of constituents in an entire row of lattice points. Point defects are of three types: stoichiometric, non-stoichiometric, impurity. In stoichiometric defects, no change occurs in the stoichiometry of the constituents. These defects are further divided into two types: vacancy and interstitial. Vacancy defects arise when a constituent particle leaves its lattice site, while interstitial defects arise when a constituent particle occupies some interstitial site. Non-stoichiometric defects lead to the change in the stoichiometry of the constituent particles. It is of two types: metal excess defects and metal deficiency defects. Metal excess defects arise either due to the anionic vacancy in the crystal or due to the presence of extra metal ions in the crystal. On the other hand, metal deficiency defect arises when a crystal becomes deficient of the metal. In impurity defect, cations in a crystal lattice leave their sites, and some foreign cations occupy the vacated site to maintain the electrical neutrality.
Okay, so that is about the defect in solids. Okay, for the video, I already put the link in the e-learnings, as well as there is another video. Okay, already put the link in the e-learning also. This, I think this type of video, but you can watch later. I think this one also a good example to explain the type of defect in the metal as well as ceramic. Okay. Okay. So we continue the effect of the defects on the properties of the materials. Okay, just another 3 slides, and then we finish this section. Okay, this part. Okay. So yeah, you already watched this video. Okay. So I hope you can understand the type of defect, especially the 0 point defects. Okay. In terms of stoichiometry, non-stoichiometry, okay, impurities, okay, just to maintain the charge, okay, the neutrality of the atoms, okay, cation and as well as anion. Okay, that's the important thing. Okay, so for the lattice defects, there are many important properties of materials. Okay, could be affected by the presence of the defects. Okay, practically all the mechanical and electrical properties is sensitive or insensitive. Is going to be changed in terms of structure as well as the properties. So if you look at here that the at the table below here, that the structure insensitive is almost we can observe in terms of the elastic constants, melting point density, okay, specific heat as well as a thermal expansion coefficients. While the structure sensitive, such as electrical conductivity, okay, semiconducting properties, yield stress, fracture stress, clip strength, like ductility, okay, and so on. Okay, so if you look at here that the significance of the point defects, okay, in terms of the mechanical properties, actually, if you look at here that it could increase the tensile strength. Okay, if we compare between two metals, cartridge brass as well as an alloy copper. This is with the 70% of copper okay, and 30% of zinc. With the cartridge brush, it's actually the tensile strength is much greater than the unalloyed copper. Okay, if you look at here, that 500 megapascal compared to the unalloyed copper 330 megapascal. Okay, so we can say that addition of one or more metals increase the strength of pure metals. Okay, this is the solid solution of could make the pure metal become stronger. Okay, however, the ductility of course is going to be reduced. Okay, because it's already mixed with the two metals or one or more two metals. Okay, okay. So in terms of the electrical properties, okay, the conductivity of the electrical also changes when addition of one or more metals. Okay, such as this one, addition of nickel atoms or impurities to the pure copper atoms is going to be reduce the electrical conductivity of the copper. So if you look at here that this is the pure copper, okay, the resistance or resistivity is low actually, so it can conduct electrics, okay, much greater compare when you add with the nickel or impurities, okay, this one. So that means if you add nickels, the resistivity is become increased. Okay, so the electrical conductivity is going to be reduced. However, if you add the germanium's impurities atom to pure silicons, okay, so the electrical conductivity will increase greatly. Okay, compare with the pure silicon. Okay, so this is the comparison in terms of the electrical properties. Okay. So, any question about the crystalline imperfections in metals as well as ceramics? Okay. Any questions? Just I think this part is more to general information, and maybe the most important thing is home rotaries. Okay, rules. Okay. Uh, how to observe or predict either your uh, materials, okay, or elements when you mix two elements. Is it 100% solubility or 80% solubility, or is a low solubility, very low solubility? Okay. What else is about the defects or crystalline imperfections? Okay. So point defects 1 0D. Okay. Lattice defects 1D, okay, or line defects, okay, 2D area interfacials, okay. So any questions? Any question about the defects? No, okay. If no questions, okay. So actually we finish this part, okay. We have a break about another 10 minutes or 10 to 15 minutes. Okay, you can have a maybe you want to drink or want to eat, okay, before we start again uh, to the new chapter, okay, about the phase diagram. Okay, so we have a break, okay, about 10 to 15 minutes. Okay, okay, thank you guys. So we finish this chapter. Okay, so this one.